Now we're thinking about energy and how it applies to a system that's oscillating. First, we'll remind ourselves of a lot of energy ideas that came up in 2201. Energy is a property of a system, and a system is just a bunch of different objects that are all interacting with each other. They're all applying forces to each other. They're all feeling forces from each other. So, energy can come into that system or leave that system in two different ways, either through work or through heat flowing in or out. We'll concentrate just on energy coming into the system or being taken out of the system by work. Remember our defining equation for work. Work happens when a force acts on a moving object, and the numerical value of work is just magnitude of force times magnitude of the displacement while the force is happening times cosine of the angle between the displacement direction and the force direction. So let's imagine a system of objects where some work is being done. First case here, two things, thing one and thing two, they're both members of the system. They're both inside the system, and they're applying forces to each other. There's a force from thing one on thing two, and then according to Newton's third law, there'll be an equal and opposite force from thing two on thing one. And let's say that the force from thing two on one does work on one. Remember, the numerical value of the work tells how much energy is transferred when the work is done. If the numerical value of work is positive, then the thing that was feeling the force gained that much work. And if work is negative, then the thing that was feeling the force lost that much work, or lost that much energy. But let's say the work done on thing one is positive. Positive work means thing one gained some energy, and that energy has to come from somewhere. It doesn't just appear out of nothing. The way things work is that the energy gained by this thing was given to it by the source of that force that did the work, thing two. When two things interact and energy is exchanged by work, one thing gives up energy, the other thing gains energy. That is, work done on one is positive, means it gains energy. Work done on two is negative, that means energy is taken away. The energy taken away by two is taken away from two is then given to thing one. But overall, if we look at the whole system overall, the total amount of energy in that whole system has not changed. You've moved some energy from here to here, but that energy that moved around stayed inside the system. The total energy did not change. Zero change in the total energy of this system. But now let's imagine the same kind of thing, except now thing two is outside the system. So thing two still applies a force to thing one, and then Newton's third law, that means that thing one is applying a force to thing two still. And we'll say, just like in the previous case, that force from two on one does positive work on thing one. In other words, it gives some energy to thing one, and that energy came from the source of the force that did the work. Thing two lost some energy, and the energy was gained by thing one. Thing two had energy taken away from it because negative work was done on it. Negative work, remember, means energy is taken away. So this has some energy taken away from it, and this gains that much energy. So what happened is that some energy that was outside the system has now been put inside the system, and the total energy of the system has actually increased because there was work done by an external force, right? A force that had for its source something outside the system. And in general, that's the way work changes the energy of a system. We can write it this way, right? The total amount of work done by all the external forces put together, or the total work done by the net external force, just add up all the forces acting on things in the system that come from somewhere outside the system. That total amount of work can change the energy of the system, and that's the only way work can change the energy of the system. Right? In a situation like this, work is still done, but it just moves energy from one piece of the system to another. Here, work is done, but it moves energy from outside the system to inside the system. So, when we're thinking about energy considerations, we always have in the back of our mind external forces doing work. So one of the things that we'll always want to do is identify the forces acting on an object and then decide whether those forces are internal forces coming from somewhere inside the system or external forces coming from outside the system. And of course, to do that, we have to decide what's in the system in the first place. And we have four nice rules to help us decide what should be in the system and what doesn't have to be in the system. And those rules are described way back in chapter 10, but let me just remind everybody of those rules. Rule number one, anything that's moving is going to have kinetic energy, so we have to include that in our system. So moving things should be included in the system. And furthermore, if the movement involves a change in elevation, then that means gravitational potential energy will change. And gravitational potential energy, like any other kind of potential energy, is energy that comes from two objects interacting by a force. In the case of gravitational potential energy, obviously, the two interacting things are two masses acting on each other with gravitational forces. Usually a moving thing and the Earth. So whenever we talk about potential energy, we always think of that potential energy as shared by the two things that are interacting. So if we do have to think about gravitational potential energy and want to include that energy as part of the system's total energy, we have to include both things that share in that gravitational potential energy. So we include not only the moving thing, but the Earth. And now, thinking about a second kind of potential energy, there's so-called elastic potential energy stored up in any object that is any elastic object that is stretched or squeezed or twisted or distorted in some way. Like, for example, a spring. An elastic object, if it is, say, if a spring is stretched, for example, you applied a force to that spring while the spring was moving, so you were doing work on that spring. The result of doing that work on the spring means the spring gained some energy, and the particular kind of energy that it gained was elastic potential energy. So any elastic object that's been distorted now has some elastic potential energy, and you'll have to include that object as part of the system. Finally, if there is friction, if there's a friction force acting, then you must include specifically, explicitly, all objects that are involved in that friction, everything that feels the friction force and everything that is the source of a friction force. For example, if a mass were oscillating back and forth on a tabletop, but there was a force of kinetic friction from the tabletop on the mass, you would have to include the tabletop in the system as well as the mass. All things involved in the friction. Let's think about that just a little bit more. Let's think specifically about the kind of work that is done by say, a kinetic friction force. So you've got an object moving in one direction, let's say straight left to right, then its displacement will be just left to right. Kinetic friction always acts opposite to the direction of motion, opposite to the velocity, opposite to the displacement. So the work done by the friction is just the magnitude of the friction times the magnitude of the displacement, the distance traveled while the object was feeling that kinetic friction force, times cosine of the angle between displacement and friction. A displacement is straight to the right, friction is straight to the left. They're exactly opposite. They're 180 degrees apart. So here we have cosine of 180 degrees. And it turns out that cosine of 180 degrees is -1. So this is the magnitude of a force, so it is, by definition, positive. Magnitude, size, strength, those are positive numbers. Likewise, this is just the magnitude of a displacement. It's a distance between the starting point and the ending point. So a distance is necessarily a positive number. These are both magnitudes, so they're both positive numbers. Positive times -1 gives us a negative number overall. The work done by friction is negative. The work done by kinetic friction always takes energy away from the moving object. And where does that energy go? Once it's taken away from the moving object, it goes into thermal energy. Thermal energy, remember, is just the total kinetic plus potential energy of all the molecules in the system. When you rub your hands feel a little bit warmer. That's because friction is doing work on your hands, taking energy from kinetic energy from your hands and giving it to the kinetic energy and potential energy of the molecules in your hands. And when you give more energy to the molecules that make up your hands, you detect that because it feels a little warmer. Thermal energy has increased, and that's why your hands feel a little bit warmer. They are actually, it's not just feel warmer, they actually are. So what's really going on here is that whenever there's friction, there's always a transfer of energy away from kinetic energy and into thermal energy. Let's look at one particularly simple kind of oscillating system. So the total energy of a system, for our purposes, we say there are four kinds of energy that contribute to the total energy of a system. Kinetic, and then potential energy, gravitational potential energy, and then another kind of potential energy, elastic potential energy, and then thermal. So that means if there is any change in the system's total energy, that could come about through a change in kinetic energy and or a change in gravitational potential energy and or a change in elastic potential energy and or a change in the thermal energy. Now, we will imagine for our simple system just a spring with a mass connected to it, and when the mass oscillates, it'll be sliding back and forth on this on a tabletop here. But we'll keep it really simple and say there's the friction is so small that we can legitimately pretend there is exactly zero friction. Now, in our system, what exactly should we include in the system? Go back to the four rules. When things are oscillating, the mass is moving, so we need to include that in the system. The movements don't involve any change in elevation, so there's so the gravitational potential energy actually doesn't change. We can completely ignore that, and we don't have to include the Earth as part of the system, even though there actually is, of course, a gravitational force on the mass. There is an elastic object, a spring, that gets stretched and squeezed as the oscillations happen, so that thing will have elastic potential energy, so we include it in the system. And there's no friction, so we don't have to include the tabletop. If there were friction, then of course the tabletop would be a source of a frictional force, and in that case we would need to include it. Because when it does friction, when it does the negative work of friction and takes kinetic energy away from the moving thing and gives it to thermal energy, it's going to give it to the thermal energy of the tabletop will increase, and also the thermal energy of the mass. So if we want to have all of that thermal energy counted as part of the system's total energy, we have to include all the things that will get an increase in thermal energy. Okay, now, work is done by external forces. So to decide whether they're, and work done by external forces is what changes the energy. So to decide if there's an energy change, we have to see if there are any external forces and then see if they do work. Well, when there's no friction, there are just three forces that we have to worry about. There's the weight of the mass, there's a normal force from the tabletop on the mass, and then there's the spring force. That spring force could be either pushing or pulling, could be pushing to the right or pulling to the left, depending on where exactly the mass is. But that's an external force because its source is the Earth, which is not part of the system. And that's an external force because its source is the tabletop. It comes from the tabletop. It's a push from the tabletop on the mass. That is an internal force because its source is the spring. Its source is inside the system, part of the system. So in this case, you have two external forces. If either of those do any work, the total energy of the system must change. Because remember, the total work done by all the external forces is 0. However, those two forces don't do any work. And that's easy to see just by using our defining equation for work. Work done by the weight, for example, is magnitude of the weight times displacement while the oscillating mass is feeling that weight, and cosine of the angle between the displacement direction, which is going to be either to the left or right, but horizontal always, and the weight force, which is always down. Displacement and force are perpendicular to each other, so they're 90 degrees apart. Cosine of 90 degrees is 0. So that's an external force, but it does no work. So it won't change the energy of the system. And for exactly the same reason, this external force will not do any work. Because just like the weight, this force is perpendicular to the displacement. And so when we figure out what the work done by the normal force is, the cosine factor will again be the cosine of 90 degrees. The cosine factor will again be 0. So what do we have in this case? Work done by external force is 0. So there's no change in the energy of the system because work done by external force is how a system changes its energy. So that never changes, but individual types of energy within the system could change just as long as all those changes cancel each other out, so the net change in energy is 0. Let's look at this example. Let's say you've pulled that mass away from its equilibrium position. Equilibrium position is right here, so there's a displacement to the right, of that mass. The spring is stretched, so it's going to try to pull back. It's going to try to snap back to its original shorter length. Trying to restore its original shape is what elastic objects do when they are distorted. And in trying to snap back to its original shape, it's going to pull to the left on the mass. So as soon as you let go of the mass will start to speed up. The mass will start to gain energy, but at the very instant you let go, it doesn't have any speed yet. So at the initial moment, the very start of the process that we're going to look at, the velocity is 0, and then the velocity starts to increase. And then that's the initial state. The final state, let's say it's been oscillating back and forth, but we're going to look at half an oscillation. The half oscillation that starts when the mass is over here and ends when the mass is over on the other side, when it's come to a stop on the other side of equilibrium. So let's say initially, we'll say A is the distance from equilibrium to the mass right when this process starts, in the final state, the mass is now to the left of equilibrium as far as it's ever going to get away from equilibrium. It'll go no farther to the left. This is the maximum distance away from equilibrium on the left-hand side. We'll call that distance B. But in that final state, since it's not moving any farther to the left, and it's not yet started to move to the right either, at that moment it has come to a stop. Final velocity is 0. So the process that we're looking at takes half a cycle, starting when the mass is over on one side of equilibrium at its maximum distance away, and then ends when the mass is on the other side at the maximum possible distance away from the equilibrium point. So over that process, what kind of energy changes have we seen? Well, delta anything is always final value minus initial value. So really we're just comparing, for instance, the value of kinetic energy at the initial moment to the value of kinetic energy at the final moment. And in that case, the initial speed was 0, so the initial kinetic energy was 0. The final speed is 0, so the final kinetic energy is 0. So there's, between start and finish, there is no net change in kinetic energy because it's 0 at the start, 0 at the finish. It's non-zero in between, but that doesn't matter. We're comparing only the initial and final states. Elevation never changes, so gravitational potential energy never changes. And that means we can pretty much ignore gravitational potential energy from now on in our simple model of an oscillating system. First this, thermal energy. Thermal energy would change if there were friction, but there's no friction, so thermal energy doesn't change. Thermal energy would be increased if there were friction, but there is no friction to increase the thermal energy. So there's no change in the thermal energy. And this is 0. equals 0 plus 0 plus 0, so this has to be 0 as well. The change in the elastic potential energy is 0, but let's write out in detail how the change in elastic potential energy looks. The change is always the final value minus the initial value, and our rule for elastic potential energy goes like this: 1/2 K, or that's the same K that appears in the equation for a spring force, times displacement squared. This is the same displacement that appears in the equation for a spring force. And notice that a displacement is a vector, so it can be either positive or negative. It can point either in the positive direction or the negative direction, but you're squaring, so even if this is negative, a negative number squared gives you a positive number, so elastic potential energy is never negative. This is the final elastic potential energy, so it would be 1/2 K final value of displacement, which means the final value of displacement is minus B. It's displaced in the negative direction, B meters away from the equilibrium point. And then the initial 1/2 K times the square of the initial displacement away from equilibrium, and the initial displacement away from equilibrium was plus A. It was on the positive side of equilibrium, A meters away. But we know that this is the change in elastic potential energy, which is 0. So this must be equal to this, which means simply B equals A. In other words, the maximum distance away from equilibrium on one side is just the same as the maximum distance away from equilibrium on the other side. Not surprising, but what that does tell us is that if we think of A as just the initial distance by which you stretched the spring in the first place to start the oscillations, then that initial stretch will determine the amplitude from there on, as long as there's no friction. When there is friction, we'll talk about this in class. When there is friction, it gets a little more complicated. Now, one last thing about that amplitude. And when we talk about amplitude, we first want to define a new thing called mechanical energy, which is just the sum of the kinetic plus potential energy in the system. So in other words, the total energy of the system will just be the mechanical energy plus the thermal energy. Now let's keep thinking about our system in which there's no work done by external forces. We're thinking about the same system, so there's no change in the total energy. And no friction, so there's no change in the thermal energy. So any change in total energy comes from a change in kinetic plus a change in elastic potential plus a change in thermal, or we could just as easily say any energy change comes from a change in mechanical energy plus a change in thermal energy, right? If there is any change in this, it could come from a change here and or a change here. But since there's no friction, nothing happens to the thermal energy. And we know that there is no work done by external force, so there is no change in the total energy. So therefore, there is no change in the mechanical energy. The mechanical energy, kinetic plus potential, stays constant. And so we can draw one important conclusion from that. Let's imagine our system right at the start when you've pulled the mass a meters to the right away from equilibrium, and then at that instant you let go. So it starts from rest. So there's the initial state. Now the final state, we will say, is when the mass is back at equilibrium. And it's been gaining speed all the way from here to equilibrium, so it does have velocity, or the velocity at equilibrium is not zero. Let's think about the mechanical energy, which is staying constant in this situation. Here at the beginning, as always, mechanical energy is kinetic plus potential. At the initial moment, the velocity is zero, so kinetic energy is zero. But there is potential energy because the spring is distorted, stretched, and that's 1/2 k displacement squared. So that's what the mechanical energy looks like at this moment. This is the numerical value of mechanical energy at this moment, but mechanical energy stays constant. So this is the numerical value of mechanical energy always. And when you look at that equation, you see that the mechanical energy is directly proportional to amplitude squared. You can imagine starting the oscillations by pulling the mass different distances, and that the distance by which you pull the mass is what determines the amplitude. So you can imagine giving that system different amplitudes of oscillation, but it's the same spring all the time, so k doesn't change. So you just have some variable equals constant stuff times some other variable. You've got proportionality. And this turns out to be an important proportionality. Amplitude is a way of keeping track, so to speak, of the mechanical energy of the system. A big amplitude of oscillation corresponds to a large amount of mechanical energy, and an oscillation with small amplitude corresponds to a smaller amount of mechanical energy. And more to say on that in class and in the next